All right, why don't we go ahead and get started? So I want to welcome everybody who came here today. We're going to be doing a webinar on advanced mixture design of experiments. This is the second webinar in a two-part series that we have. We have a crash course in Mixture DOE that we periodically give. And this is the second part that we give once in a while, which is a little bit more advanced. I do want to apologize if anybody was here a few weeks ago when we had some technical issues that resulted in sound going out in about 10-15 minutes into the presentation. So we're going to give it a second shot here. And for those of you that don't know me, my name is Martin Bessener. I'm the president and CTO at Staties. If you'd like to reach me directly, you can use this email address here, martin@staties.com, and I'll be happy to take a look at what you send in. However, on the next slide, I'll give you a better email address to use if you have any specific questions about the software or about anything that was said in this webinar here. So with that, why don't we go ahead and jump right in? So just some housekeeping things, as always, because we have a decent sized group here, we have everybody muted to avoid any audio disruptions. However, if you have any questions, you can post them using the questions or the chat widget in GoToWebinar. I try to periodically peek to see if there are any outstanding questions. If they are not answered, I'll try to answer them afterwards, or you can always go ahead and email us here, stathelp@staties.com. This is our statistical helpline, and it is monitored by all of our statisticians and consultants, so that includes me plus several other people. So if I'm, for example, not around, somebody else can jump in and get to your question quicker than I may be able to. And as always, we will have the slides and a recording available of this webinar, probably later today or sometime tomorrow. So if you have to sign off early or you want to review something, this will be available freely on YouTube, on our website, and whatnot. So just some latest news from Staties. Just a couple things. We do have our new software, Staties 360, which was launched at the end of October 2021, and it's essentially a pro version of Design Expert. At the end of this webinar, I'll show one or two features that are relevant to mixture design of experiments, but we encourage you to check it out. And of course, there's only so much we can do in a 45 to 50-minute webinar. If you find this material interesting and you want to get a more rigorous, deep understanding of the topics that I discuss, we do have a live web Mixture DOE workshop. This is kind of our classical workshop, essentially 2 full days or 4 half days, where it's instructor led. They go through lots of examples, lots of applications, and go through all of these topics that I discuss in a lot more detail than I have time to do so today. So I do encourage you to check that out if you want a longer, more rigorous course. On the other hand, we do have a new essential series that we launched for our workshops this summer. We often get questions about, well, I want to take a workshop, but I don't want to devote 4 mornings or 5 mornings or whatever to sitting in a classroom or sitting on the computer. So what we do is we now have 2 half-day mini classes, basically, of hands-on learning. So it's if you've taken our mixture workshop maybe in years past and you just want a quick refresher, you feel free to check out any of the essential series. And we do have one that's just on optimal tools for formulation development, also known as Mixture DOE. So you can head to our website, head over to the training section, and all the information is there. Okay, let's get into the actual meat of the presentation. So we do have, so this is meant more of as an intermediate to advanced webinar. However, we will spend about 10-15 minutes just recapping the content that I talked about in the first part, the crash course. So we'll spend about 10-15 minutes recapping that. Then we'll dive deep into actually designing Mixture DOE. So mostly focused on optimal design, how to set up these computer-generated designs, as well as talk briefly about some other advanced mixture DOEs you may run into, like split plots, combined mixture designs, space filling designs, and so on. Then the part that everybody likes is the practical tips and tricks here. So I've been doing this work on a near daily basis for about 11 years now, and I've seen pretty much every mistake that is possible to make. So I've tried to condense it into 10 of the most common mistakes I've seen that hopefully you can avoid in the future. And then finally, I'll just wrap up with some other resources that you can use, as well as look at Statis 360, just look at one or two features that are relevant to Mixture DOE. So, okay, let's get going here. So I always like to start with, what is a mixture experiment? Because we get even statisticians that have master's degrees in statistics that sometimes are not quite sure when they need to use a mixture experiment. So I always like to start with this. And I always like to use very simple food examples in my presentations because we have a very wide variety of R&D people here, people from aerospace to paints to food. So I like to choose very simple examples that everybody can kind of understand. So pizza. So let's say that we're manufacturing pizzas in our factory and we're deciding what cheese we want to put on the pizza. And after consulting with customers and food scientists and the people that control the purse, we've decided that we are going to blend 3 cheeses together: mozzarella, provolone, and white cheddar. Okay, and it turns out that when we want to try, each of these cheeses on their own, we want to try combinations of 2 of them, we want to try combinations of 3 of them, and so on. However, ahead of time, it's been decided that each pizza will be topped with a total of 6 ounces of cheese. So that's not going to change. Every pizza, no matter what type of cheese we put on it, it's going to have roughly exactly 6 ounces of cheese on it. So that means we could put 0 to 6 ounces of mozzarella cheese on there. We could put 0 to 6 ounces of provolone and 0 to 6 ounces of white cheddar in theory. But notice that whatever 3 cheeses we choose, whatever 3 amounts we choose, they absolutely have to add up to 6 ounces total. So if I put 2 ounces of mozzarella cheese on there, provolone plus white cheddar has to add up to 4 ounces. So there's 4 responses: appearance, taste, texture, and then of course the all-important cost. And as you may notice here, the components of the cheese blend cannot be set independently of one another. Okay, so once again, this is really what makes or breaks the decision on whether you need a mixture DOE. Is, do any of the things that you're blending together or setting add up to a fixed total? In this case, all 3 things that we're putting in, the 3 cheeses that we're putting on top of the pizza, have to add up to 6 ounces. That is really, if you see that what we call it as an equality constraint, meaning some things have to sum up to a fixed total, you have a mixture experiment. So a mixture DOE would look something like this. So notice that, for example, the first pizza I'm making is this one. I'm putting 0 mozzarella cheese on there and 3 ounces of provolone and 3 ounces of white cheddar. In the second pizza that I'm testing, I'm putting 4 ounces of mozzarella cheese on there, 1 ounce of provolone, 1 ounce of white cheddar, and so on. So notice again that the DOE here, the actual experiment, everything sums up to 6. If I were to take that spreadsheet, that DOE, and plot it into 3D space, I would get the points that look like this. And if you happen to have a very keen eye, you can see that all of the points, despite there being 3 components and this being a 3D space, I could actually draw a triangle inside this space where all of the points lie. So they all lie along this triangle here. So a much nicer picture is this one here on the right. Okay, so what this is telling me is that even though I have 3 things that I'm setting, really I only have 2 dimensions. And the reason why is this, because if I set 2 of my components, the third one is set automatically to force the sum to be equal to 6. So what I'm going to do is I'm going to take this this triangle here, and I'm sorry I don't have the touch screen here with me, so I'm kind of using my mouse to draw, which is not great. But if I take this triangle here and I flatten it out, I basically put it on flat paper, I end up seeing something that looks like this, and this is what a typical mixture design space looks like. It's called a simplex, or more casually, a triangle. And you can see that the red points are where we are doing runs. So we're not working in this square space like we would with the factorial design. Because of this equality constraint, we actually have this new simplex space. So as you can see here, the red points denote runs that we're doing. The vertices here are essentially quote unquote one cheese blends. They're not really blends, it's just we're testing one cheese at a time. The edges are blends of two cheeses, and any of the points on the interior here are blends of all three cheeses. And anytime you see a number next to a point, that means we're going to be doing that point more than once. So independent replicates that we're doing, just like you would in maybe a factorial design with center points. Okay, so this looks a little bit different, but really the idea is the same. So just to wrap up, identifying a mixture experiment. So blending experiments should usually be set up as mixture DOE, but not necessarily always. I don't want to say, well, anytime you're mixing something together, it should be a mixture experiment, because that's not always true. Sometimes people will vary concentration of the components, or they will actually vary the amount of the components that they are putting in, instead of varying something like the weight percent or the volume percent or proportion total. If you've ever done concentrations, you'll see that those typically don't sum up to a total concentration. You'll have 3 or 4 components. They go from a low to a high concentration, and that's it. Or if you're varying the actual amounts you're putting in, like you're going from 0 to 10 grams of each component. In a situation like that, you might be better off with you likely will be better off with a response surface experiment. But if you're varying weight percent, volume percent, any of that stuff, a mixture design is probably going to serve you much better. So the key to verifying whether you need a mixture design is to determine if any of the columns in the design plan, so when you look at your spreadsheet, if any of the columns add up to a fixed total, you have a mixture. And just one little caveat here, you may be in a situation where part of an experiment is a mixture, like a cake formulation, but then you might have factors that are non-mixture factors. So things like the temperature at which you're going to bake the cake formulation, or how long you're going to cook it in the oven. This is called a mixture process design, and we're going to talk a little bit about it later in this webinar. Now we know when to choose a mixture design. So let's get into the actual DOE here. So there are really 2 basic categories of mixture DOEs. We have simplex-based designs, which we also call canned or textbook designs. And we have optimal computer-generated designs, or these are sometimes called custom designs. Okay. In practice, and as I said, I've been doing this for over a decade on a near daily basis with probably hundreds of people in R&D at universities and whatnot. And I would say 99% of the designs that I use are optimal computer-generated designs. It's pretty rare that I use a simplex design, but I'm still gonna put a picture of one just so you can see what's going on here. Okay, and there's a reason why we're gonna spend the middle third of this webinar just on optimal computer-generated designs. So these are simplex designs. They're canned, which means you can't modify them all that much, and they're very straightforward. But in order to actually be able to use a simplex design, one of the following conditions has to hold true. All the components go from 0 to 100%. Now, is that realistic? Well, I mean, if you're doing a chemical reaction, does it make sense to test levels of the mixture where catalyst is 0% or where catalyst is 100%? I mean, those are basically, you get no data. You don't get suboptimal results. You just get useless data in those situations. So pretty rare, but sometimes it appears, especially in like food, when you're blending together like 3 oils or something, you could be in a situation where everything goes from 0 to 100%. Or all the components must have the same range. So if you go from low to high, if that distance is the same for all of your components, you could use a simplex-based design. And this is once again not all that common because in almost all real world problems, the components are going to have ranges that aren't the same. Okay, so if you look at a picture, this is a 3-component simplex lattice design, and the one here on the right is a 4-component simplex lattice design here. So they look nice, they're very pretty, everything's spaced evenly, but we don't really use them all that much. So as I said, this basically sums up what I just said. So simplex designs are very restrictive and they don't have a ton of use in the real world. It rarely makes sense for all components to go from 0 to 100%. Like, would you make a bread dough formulation that's 100% yeast and 0% of the other components? Okay. And it's also somewhat rare that all of your components have the same range. So my tip is this is a tip we always give at Staties. I mean, every workshop, every webinar, don't force your components, don't modify the ranges of your components to fit one of these simplex designs. Sometimes I'll see people that force the ranges to be the same just so they can use a simplex lattice design. And then what happens is some of the components, the range is too narrow, some of the components, the range is too wide, and they don't get the maximum amount of information that the experiment's able to give them. So generally, we highly recommend against doing it. Instead, a better option is an optimal computer-generated design, which is also known as a custom design. And if in our software you absolutely have to use a simplex lattice design, you can find it here. When you open the software, you'll see the mixture section here and the simplex lattice. All right, so here is a much more realistic example of something that you might come across when you're doing your own work. So let's say we have 3 components. Component A goes from 0 to 20%. Component B goes from 0 to 50%. Component C goes from 0 to 50%. However, there's more. We also want A plus B to be greater than or equal to 10%. What that means is basically that A and B cannot both be at their low setting. I need to have at least some of A or B. I need to have at least 10% of the mixture be A plus B. Okay, so it's impossible for A and B to be both be 0 or both be 3%. And then just to make things even a little spicier here, we see that the ratio of B to C has to be between 1 and 1.5. So what I'm saying here is that I can have B, I need to have B at least as much B as I do C, but I can't have like too much B relative to C. B relative to C has to be less than 1.5. Okay. And then finally, as always, I have this equality constraint where all 3 components have to sum up to 100%. All right, so if I were to plug this into Staties 360 or Design Expert, here's what the actual space would look like. So this triangle here is the full 0 to 100 simplex space. This little white region here is the design, is basically the set of blends that satisfies all of those constraints that I put, that I placed in the previous slide. And what I'm going to do is I'm going to take my magnifying glass here. This guy right here is going to take his magnifying glass and he's going to kind of zoom in on this space, and then we get this space here. So what that does is basically that draws a triangle around this this quadrilateral, this what is it, 4-sided figure here. Okay. So obviously, if you wanted to use a simplex lattice design, you'd have to use this whole triangle here, or you'd have to use like a triangle somewhere in here. So this is a case where an optimal custom design is a total slam dunk here. So if I were to use, this is just a little preview, but if I were to use the software to create an optimal computer generated design, it would look something like this. Okay, so I take my space, I take all of the constraints, all of the ingredients, I put it in our software, and I get a design that looks like this. So you see the red points are basically where I am doing a run. Okay, so you can see there's some points here along the edges. There's some points on the interior, there's some points on the vertices, so you get and there's of course some replicates, so some runs that are being done more than once. Okay. So why don't we dig deep then into actually setting up these designs, optimal computer generated designs? How do we set them up? How do we go through the process? And finally, some FYIs on other types of designs you might run into in the future. So here's what this section is going to consist of. So, and I do want to give a warning here. This is going to focus only on setting up the designs. So building the DOE. Analysis is usually pretty straightforward. So whether you have a simplex design or whether you have a really complicated mixture design, the analysis and building models and looking at graphs really doesn't change much. And we have tons of resources available on our YouTube channel, on our website, that go through the step-by-step how we analyze these designs. Of course, our workshops and training courses also do the same, but we're going to basically get to a point where once we build the design, we move on to save time. So we're going to do a deep dive on optimal computer generated designs. We'll talk a little bit about space filling designs, which are unique to Statis 360. We'll talk a little bit about mixture process designs. So when you have process factors on top of mixture components, and then just a couple other designs you might run into in the future. So we saw an example where an optimal design would be very useful. So here is the general kind of DOE flow chart that you should be, and this is probably not super unique to mixtures, but it's the one that we're going to follow today. So the first one, and this is by far when you're doing DOE, the single most important step that's probably going to make or break whether the DOE is successful or not. Choose the mixture components and set their ranges. Okay, so you have to know what you're going to be blending and what are the lower and upper bounds of what you're going to be blending. If you choose these bounds to be incorrect, you might not have a region, a DOE space that actually encapsulates the optimum that you're looking for. And with mixtures, this is especially complicated because of the fact, well, if I want to add more of my first component, you have to add less of either your second, third, fourth, fifth, or sixth component, and so on. So it's like you put more of one component and you have to figure out, well, because of the equal sign, which component is going to be put in lesser quantities. Okay, so by far, this is, in my experience, the single most important step. And this is 10 times worse when you're dealing with mixtures because of the equality constraint. And this is largely not a statistical issue. Choosing what to blend is more of a subject matter thing. Same thing with choosing the lows and highs of each component. That's more of a subject matter issue. A statistician generally is not going to be able to contribute all that much to this discussion. Then you want to choose what's your model of interest, meaning once you generate the design, the spreadsheet, what's kind of the highest order model that you want your design to be capable of handling. So if you're doing screening, maybe linear model might be good enough. But if you want to find how your components are interacting with one another, is there any curvature in the data, you'd probably want to design for a quadratic model, and so on. Finally, the all-important question, how many runs do I need? And as well as when you're doing optimal designs is what types of runs do I want to put in the DOE? Finally, there's some build parameters you need to set. You need to figure out what it is that you're going to be measuring, and then you need to click the finish button to generate the design. So we're going to do this as a demo rather than going through a bunch of theory here. So in this example, what we're going to be doing is we're going to be formulating a fruit punch. And this fruit punch consists of 5 possible juices that we can blend. So we can blend grape, watermelon, orange, apple, pineapple. Each juice blend can be independently formulated, and so we don't have to do like big batches or anything, and will be tested and rated by a panel of experts. Turns out that we have a budget of 40 runs, which is largely determined by how many of these we can test, because making a blend of fruit punch is pretty quick. So how can we build an optimal design here? So let's go through that workflow that I had just talked about. So the first thing is to choose the mixture components and set their ranges. Now this, I believe, is a real example that we had from decades ago. So here were what these juice scientists decided to blend and the ranges. They decided, well, we're going to have grape go from 0 to 10%. So notice 0 is a lower bound, so there could be blends with no grape juice in there. Watermelon from 20 to 60%, orange from 10 to 40%, apple from 10 to 20%, and pineapple from 5 to 15%. The total of the 5 juices needs to sum up to 100, I believe it was volume percent, because they were making fixed volumes of juice. Okay, so simple enough, hopefully. So determine the model of interest. Well, as I said, linear mixture models can only detect like linear blending properties. So in other words, weighted averages of 2 or more components. These designs are pretty good for screening or for getting a rough idea of what's going on, but they're not going to tell you about any non-linearities, any interactions, any interesting curvature that's going on in the model. So the food scientists had a reason to believe there was nonlinear blending in the mixture, so they chose a quadratic mixture model. And then choose the number of runs in the experiment and define the properties of these runs. So the run budget was determined to be 40 runs, and the experimenters decided to do 30 runs in the first pass of the experiment. So even though they had a budget, what they were doing is they were essentially setting aside 10 runs in case something went wrong. So they basically figured, well, maybe if I chose my components to be wrong, I'd have a little bit of runs left over later that I can kind of use to patch things up. Okay, so what I'm going to do is I'm going to actually move over to the software here so you can get an idea of how you would do this. So what I would do is I would click on New Design. I would go to the Mixture section. Now notice how it defaults to Simplex Lattice, but if I try to set this up as a Simplex Lattice design, it's going to complain and say that the bounds don't match up. So I'm actually going to go to an optimal design. Let me make this text a little bit bigger here so you can kind of see what's going on. I'm going to do 5 mixture components, and this is the and I'm going to have them sum up to 100%. So I have my grape juice, which goes from 0 to 10. I have my watermelon, which goes from 20 to 60. I have my orange, which goes from 10 through 40. I have apple, which goes from 10 to 20, and then I have pineapple, which goes from 5 to 15. Okay. If I had any constraints that involve 2 components, like for example, grape plus watermelon has to be equal to this, or if I had a situation where maybe I had a ratio constraint, I would use this edit constraints button here to enter them. Okay, simple enough. Now, this is the screen in our software where we get a ton of questions, and we're going to spend a few minutes going through all of this stuff here. So I'm going to move back to the slides here really quick, but this is where we're going to be setting the number of runs in the experiment, and we're going to be defining the properties of runs, meaning what type of runs do we want. And then we also need to, so this is where we set the number of runs. And then finally, we need to set the remaining build parameters. So that means, there's some kind of tweaks you can make to how our software will build the design. Okay. So let's talk about choosing the number of runs. So that is, again, this section here on the right. And I'll go ahead and show you in the software, it's this section right over here. Okay. So, first thing that you'll see is that there's this thing called required model points. Okay. And this is determined by the model that I'm interested in fitting. Since I chose a quadratic mixture model, I need at least 15 points. That's basically like saying, well, if I want to fit a straight line, I need 2 points. If I want to fit a quadratic line, quadratic curve, I need at least 3 points. So a quadratic mixture model has 15 terms in it, so I need at least 15 runs just to mathematically be able to fit what's going on here. These model points are chosen in a way to optimize this optimality parameter that we choose here. So what States 360 is doing here is it's trying to build the best predictive model here. That's what this I optimality means. And these model points, essentially these runs, are arranged in a way that tries to give you the most robust, the best predictive model. Okay, if you want to add some runs to your design, we have these additional model points. The way that the algorithm will add them to the design is to try to make the design as, have the best predictive properties as possible. Our software generally also puts in these lack of fit points. These are, after the model points are assigned, the software will look for any big gaps in the design space and put a point there. So what that does is that essentially ensures that there aren't any enormous gaps in the design space where you don't have any information. Finally, replicates, meaning, if you want to do some runs more than once, for like an estimate of pure error, or if you want to just test to see if you can repeat, for repeatability, well, that's what replicates would be put in for. Okay, we generally suggest a minimum of 5 lack of fit points and 5 replicate points. If you have any extra budget, we would suggest putting in additional model points here. Okay, and as I said before, you need to choose the model. By default, Design Expert and States 360 will do quadratic models for mixture experiments. If you're in a situation where you want to block, meaning like you have lots of raw material, or the experiment's done over 3 different days, or it's done at 2 different sites, or tested on 2 pieces of equipment, you could add, you can add blocks here. Okay, so this is once again, so if, for example, we had a budget of 30 runs, what I would like to do is I would like to add 5 more model points here. Okay, and then finally, the response is taste, which I believe is on the typical 1 to 9 scale here. And then when we click finish, we generate the design. Okay, so it's going to take a second, and there you go. Now I just want to show off one new feature here that is super useful. When you're blending together juices, I mean, it's not always possible to measure out to 5 decimal places. Okay. It's really, the algorithm doesn't care about your feelings or what you're able to do or your limits and hardships and whatnot. It just cares about mathematically what gives the most predictive model. So what we do is we have this round columns button now where you could round off the entire mixture to a fixed number of decimal places. So defaults to 2, but some people might only be able to round off to 1 decimal place. And rounding in mixtures is especially painful because of the fact that when you round a component up, there's more than one way essentially to round components because of the equality constraint. So we do have this round columns feature in newer versions of our software that will automatically do that for you. Very well received feature here. And then you would go ahead and okay, blend each of these juices, type in the responses here, and then you would analyze as you normally would. Okay, so some tips and tricks on choosing a design size, how many runs. Our software defaults, we put a lot of thought into what we want to choose as software defaults, which we err on the side of being safe. So if you have no strong feelings towards a particular design size and the defaults that we give you are doable, we suggest starting with those. What usually happens though is people see our defaults and they say, well, this design's a little bit too big. Okay, if you need to cut runs, lower the replicates and lack of fit points. A minimum of 3 for each is recommended. If you cannot afford any, I would just skip them and set them both to 0 at that point. Okay, you're not going to get a lack of fit test, and you might have big gaps in your design space, but I mean, that's probably better than not being able to do the experiment at all. You could also consider lowering the model order, but again, generally, unless you're doing screening, we really don't like to go below quadratic. Now, on the other hand, if you have lots of extra runs, like you have lots of budget for your experiment, you could consider increasing the model order before adding extra model points. So something like, maybe if I were to redo this experiment here, so if I go to new design, I reuse all of my factors and whatnot, maybe you could consider going up to something like a special cubic model, okay? In this case, it's going to add an extra 10 runs here, so maybe that might be a little bit too big, but you might want to do that in case you have some really tricky behavior in your data. A higher order model might model it a little bit better, might catch that behavior. Or you could, of course, add extra model points, add extra replicates or lack of fit points. Generally, I don't mind going up to something like 10 to 15 lack of fit points. I mean, if you really have a ton of money and time. But replicates, I generally really don't like going beyond 5 or 7 because you really, beyond that point, you don't get much more information about the error in your system, and you're really not getting more information about the model. Finally, use the fraction of design space. So that is located, I'm just going to go ahead and I have to sorry, I didn't save this model, so I need to do a quick rebuild here, but you could use the fraction of design space here in the evaluation, and that'll give you some preview about how good your design is before you actually do the experiment. I will be doing a webinar in a few weeks here specifically on this topic, on fraction of design space for mixtures and response surfaces, power, evaluating your design, how to fix any problems ahead of time. I'll be doing that in about I believe it's in about 2 weeks. So if you have any doubts about that or you want to learn more about that, keep an eye out for that webinar. Okay, so that takes us through the entire build process of an optimal design. Now I'm going to mention a couple of other designs that you might find useful. So one might be space filling design. So these are another category of mixture designs, and what they try to do is basically fill a design space without leaving any large gaps. Okay, so intuitively speaking, the way I like to say is these are designs that look nice. I mean, they're not always the best designs, but a lot of people say they look very, very nice and very pretty. Okay, so this is an example of a design that doesn't really, that doesn't have any large gaps, where the points are spread apart nicely. So it looks space filling. This is an example here on the right-hand side of a design that doesn't look very space filling. You've got a cluster of points over here in this corner, and then you've got these very large gaps here in the middle where there's, and you have this corner here that's totally empty, this corner here that's empty, where you're going to get a lot of really good information about the right-hand side of the design space. Okay, anything over here, you're going to get a lot of really good information, but anything on the left, you don't get much information about what's going on over there. So space filling designs can be used in a wide variety of cases. So they're very popular in computer experiments where you're doing simulation and you don't want replicates because the same run, the same set of mixture components or factors is going to give you the same exact output. Okay, so if you have a deterministic response as part of a computer simulation, don't do replicates. A space filling design is going to give you usually maximum information in that case. One case where I love using space filling designs is when you're very early on in the whole process and you're just doing exploration. You're doing exploratory studies. So you're in a new design space. You might have components you're not familiar with. You're testing the bounds from low to high. You're essentially basically doing range finding, figuring out where to experiment. Space filling designs will spread the points apart as far as possible without leaving any big gaps. So essentially, you're going to get a good amount of information about a new design space. You might see, oh, some of the vertices just don't work. That's where I really like using space filling designs, is because they give you lots of information in that case. You're not really looking to do a rigorous model. You're more of just looking to exclude certain areas of the region. Finally, if you have a sharp peak or a very sharp valley in your response, a space filling design has a better chance of catching it since there are more unique design points that are evenly spread apart. So here's an example. If I were to do something like a typical optimal design, I might get, something that looks like this, where I get two, maybe 2 runs here, 2 runs in the middle, and 2 runs here at the end. Notice that my response might have a sharp spike in the middle, and an optimal design in this situation might not catch it. However, if I spread roughly 6 points equidistantly apart, sorry, this is not a great picture here, but if I spread them roughly evenly apart, there's a chance that these runs here in the middle, there's a higher probability I'm going to put in a run where that peak is, and there's a higher chance of detecting it. So here in this case, there's a spike. And if you want to increase your chances of detecting it, you need more unique runs that are spread apart. You don't necessarily need replicates. So that's a great example of where a space filling design might be appropriate. And here what I'm going to do, I'm not going to demo this in the software, but I'm just going to compare 3 different designs, 3 different optimal designs so you can see them. So I'm going to show you, here are the 3 components. A goes from 0.5 to 1, B goes from 0 to 0.4, and C goes from 0 to 0.5. This whole triangle is the 0 to 1, kind of the full design space. And notice I'm interchanging 0 to 1 and 0 to 100%. And this white region here is the region that satisfies these 3 constraints here. So what I'm going to do is I'm going to compare a space filling design, a states modified optimal design. So essentially, what is the default design we recommend? And then a mathematically pure optimal design, which some other software is default to. So here are the goods. So you can see here that a true optimal design only has a few levels here. There's not a ton of unique points. There's lots of replicates. So I'm doing 3 runs here. I'm doing 3 runs here. I'm doing 2 here, 2 here, and 2 up here. Okay, and then I have just 2 runs here in the middle. Okay, so that's like a mathematically pure optimal design. Now the one that our software would default to is the one in the middle. So notice how there are fewer replicates. There's exactly 5 of them. The points are better spread around the perimeter, and I still have some points that are done here in the middle. If I were to do a space filling design, I would get this design here on the right. Notice how here I have 0 replicates, so I'm never doing a run more than 1 time. And the points, there's good coverage of the design space. There's no big gaps here. So if I were doing like a range finding experiment, I would have a pretty good chance of getting an idea of, hey, maybe, I shouldn't be experimenting over in this upper triangle here. Now, people will say that this space filling design looks the prettiest. However, it is suboptimal if you are fitting a quadratic model, and it doesn't give you any replicates. So it doesn't really tell you anything about the error in your system and whether the model you're fitting is appropriate. So there's trade-offs. And if you happen to get everything right, meaning, in a perfect world, you get your ranges right, you get the model right, everything goes correct, then in theory, this design here on the left will actually quote unquote be the best. So there's really no best design, but the one that we default to, we try to kind of balance all of these issues to kind of guard against catastrophes. That's the one in the middle. Okay, so hopefully that takes care of space filling designs. Let's talk a little bit about mixture process designs, and I'm just going to set one up very quickly so you can see what's going on. As I said, in some experiments, a formulation might be processed under various conditions. So for example, a cake batter formulation might be baked at several different temperatures. Historically, this type of experiment, you do this in 2 stages. You'd have like the formulation team that would set all of the processing parameters to their middle value, and then what they would do is try to find the optimal formulation. And then what they would do is they would take, in step 2, they would take that optimal formulation and then start tweaking the process parameters to try to improve the results. There's a better way to do this, which is called a mixture process design. So one disadvantage of doing this 2-stage approach, which is still pretty common, is that lots of times the mixture will interact with the process parameters. So for example, like the ideal cake formula, the ideal cake batter that you want to blend together might depend on what temperature you're going to cook it at. Okay, so if you're going to cook these at high temperatures, you might need to tweak some of the formulation to get it to come out better, and vice versa. So a mixture process design, what it does is it models the effects of the mixture, the effects of the process parameters, as well as how the two interact with one another, giving you a complete picture of what's going on. And these are 99.99% of the time built as optimal computer generated designs. Okay, so here we're going to just quickly set this design up before we move on to the tips and tricks. So we have 3 components of a cake batter formulation. And then what we do is we blend them together and then bake them at a pre-specified temperature in the oven. So the things that we're varying are sugar, vanilla, and raspberry juice. Now these 3 components need to sum up to 50 grams, although each cake actually weighs 200 grams. The reason why is because you have flour and egg and all that other stuff. You're not varying that. You're just varying kind of the sweetness in the cake. And then what they're doing is they're baking them at various temperatures to test kind of what's the ideal temperature. Okay, so I apologize for our Asian and European friends, but they're going from 350 degrees Fahrenheit to 400 degrees Fahrenheit. And just a little caveat, a mixture amount experiment, if you have a case where you're varying the mixture and then you're varying how much of it you're applying, something like a fertilizer blend with differing amounts applied, it's basically the same thing as a mixture process design, except the process part is the amount that you're applying. So I'm going to set this up just very quickly, just so you can see. I'm going to close this design. I'm going to do new design. Now here I'm going to go to optimal combined designs. I have 3 mixture components and I have 1 numeric factor. So the total here, I believe, was 50 grams, and I had sugar going from 10 to 50. I had vanilla going from 1 to 1.5, and I had raspberry going from 2 to 3. Okay, complains that my ranges aren't quite right, so it adjusts them. And then here I have the temperature in the oven, which goes from 350 to 400 degrees Fahrenheit. This screen here is largely the same as in the previous example. Next, and I'm going to just set this up as taste. Okay, and it's going to build the design, and it looks something like this. So notice how this is my first this is my first cake batter formulation, and I'm going to cook it at 398.75 degrees. Again, I don't like this, so I'm going to round off temperature to 0 decimal places. Okay, and what I'm going to do is I'm going to round the mixture to let's say 1 decimal place. I could only round to let's say 2 decimal places. And there, and that's my experiment there. So for example, run 1 would be this mixture at this temperature. Run 2 would be this mixture at this temperature. So notice how the first 2 are actually replicates. Run number 3 would be this mixture here, baked at 350 degrees and so on. So hopefully you get the picture here. All right, just a couple of other designs that you might want to be aware of. Again, if we ever do a part 3 of this webinar series, these are the things I'm going to be talking about here. You could have double mixture designs, so things where you have 2 separate mixtures that you're ultimately combining. One classic example is of a double mixture is where you have a cake batter formulation and a frosting formulation. And then at the end, you're putting the frosting on the cake. The 2 mixtures might depend on one another. Like for example, if you put a ton of sugar in your cake batter, you might not want to put as much sugar in your frosting and vice versa. So lots of cases where you might have several mixtures you're blending together. Split plot designs, up to this point, we've assumed that you could do each blend independently. You don't need to prepare big batches of stuff. If you do have formulations you have to prepare in batches, or several independent formulations have to be processed at the same time, meaning like I have to bake 4 cakes in the oven at the same time, I would use a split plot design here. And then finally, at the end, you could also have a mixture of mixtures design where you have several mixtures that you're blending together to form a final mixture. So that hopefully gets you started on setting these designs up and choosing the right one. So I'm going to spend just about 5-6 minutes talking about some tips and tricks that you could use in the real world. Now, these 5 here are actually from the first webinar that I do. So I'm just going to recap them quickly for those of you that may not have seen that webinar. If you want a ton of detail on each of these, please go ahead and check out the Mixture Crash Course that's on YouTube. So the first one is don't use factorial designs. I see this a lot. It's just not a good idea. Factorial designs typically only look at lows and highs. Typically what you'll do is you'll look at, you have to have a filler component and you'll leave out one of your, I really dislike using factorial designs for mixtures. Second of all, this is something that I actually saw a master's level statistician do. Don't convert to ratios so that you can avoid using Mixture DOE, so that you can use a factorial or response surface design. Now, if scientifically it makes sense to use ratios, then sure, go ahead and use ratios, like if they actually have meaning. But I would not do this as an escape route so that you don't have to use Mixture DOE, okay? You get suboptimal designs. It's a large hassle because you have to constantly convert from percentages to ratios, and then at the end you back convert and so on, and you can't have any zeros in the denominator of a ratio. So if if 2 of your components have a bound of 0 and you have 3 components, this idea doesn't even work. So don't do this if possible, unless it really scientifically makes sense. Spend a lot of time choosing your components and ranges. I already talked about this one, meaning that the largest driver of whether your DOE is going to be successful or not is, are you even experimenting in the right space? Experiment iteratively, especially for new problems. So if you have a budget of 40 runs and you really only need 30 runs to get a good design, do a 30-run design and then save the 10 runs, kind of set them on the side. If you like what you're doing, you could always do the same thing with the remainder of the 10 runs. But let's say, for example, something goes wrong, like maybe it turns out you just want to push the boundary a little bit, or maybe you chose one of the components to have a range that's too wide. You could then add those 10 runs to kind of fine tune your results based on the first pass of the experiment. Okay, so you don't have to do everything. Textbooks always present DOE as kind of a one-shot, like, here's your experiment, do the experiment, you're done. Okay, but sometimes it makes sense to do it iteratively or small chunks. And finally, master building optimal designs, because again, in practice, this is probably what you're going to be using all the time. So consider taking one of our workshops, watch this, go to look at our free tutorials that we have online, YouTube videos. We have a ton of resources available, case studies and so on, that should hopefully get you started. Now, here are 5 more tips and tricks. Now, these are a little more advanced. And this one I already talked about. If possible, analyze mixture process experiments as a single experiment, as a combined design, rather than as 2 separate experiments. Okay. People sometimes will complain, well, I need lots of runs to do that. And that used to be true until we added this thing called a KCV model into our software, which is a special model for mixture process designs. What this model does is it's basically the default that we use now, is it tries to get 90% of the information with 20% of the runs. So it's kind of that design that tries to get you, hit that elbow where you get as much information at lowest cost possible. So it's not going to model every tiny nonlinear interaction in your data, but generally for optimization, it works very well. Okay. So I believe that's, yeah, you could see that the design model for combined designs here is this KCV model. Again, if we ever get around to doing a part 3 in this series, I will be talking quite a bit about the KCV model. Next tip is always fully randomize your experiment, meaning, fully reset things, prepare one mixture at a time, process it one at a time. Now, If you're not able to do that, if you have to prepare batches or you have to put 6 things in the oven at the same time, that's fine. Just make sure you set up the design as a split plot design. When in doubt, start small and build up. So I actually talked a little bit about this on the previous slide. If possible, now I realize that I would say in at least 2/3 of the cases I see, people generally don't have a ton of excess raw materials or excess time and whatnot. But if possible, don't deplete your entire run budget in one pass if possible. Save some runs to do a second pass where maybe the bounds are tweaked, or maybe there's some big gaps you might want to investigate, or maybe the results of the first pass are perfect and maybe you can just use the extra runs that you set aside as confirmation runs, meaning just to validate the models is predicting well. And finally, use FDS plots to right size your design. So for those of you that have done factorial designs, you might be familiar with power. Mixture designs, we generally don't use power. We use something called a fraction of design space plot, and there will be a webinar available on this in just a few weeks here. And we have a ton of resources available on this as well, so feel free to check those out. So just to conclude here, Mixture DOE, it's a very powerful tool that I think, unfortunately, at the very least in the statistical field, gets very little attention. Even amongst people that do lots of DOEs, a lot of times they don't really bother with mixtures. So our software, both Design Expert and Statis 360, contains all of the latest and greatest tools for building and analyzing basic and up to very advanced mixture experiments. Again, just one take-home point. The key to recognizing a mixture experiment is determining if there is any quality constraint. There also might be process parameters giving you a mixture process experiment. And again, if you enjoyed this presentation and found it useful, I highly suggest you consider taking either our 4-day workshop or our 2 days mini essential series that we have this summer that dives into a lot more detail, as well as teaches you how to use the software so you could eventually do this on your own. So and here are just 2 textbooks. If you're interested, this is kind of the statistical Bible, quote unquote, of Mixture DOE, very technical. And this is the one that was co-written by me. That's more of an engineering-based, has more of an engineering-based approach. So not a ton of math, lots of examples, pictures, and so on. So because we are short on time, I am going to skip this section here. It is available if you want to see it. We have a ton of Statis 360 videos on our YouTube channel. Feel free to check them out. So I do want to thank everybody for sticking around. I know we went almost 1 hour here this morning or afternoon or evening. So once again, if you want to contact me personally, you can reach out to martin@statis.com. However, we do have that stathelp@statis email, stathelp. So that's stathelp, all one word, @statis.com. If you have any statistical questions, I highly recommend using that email address instead, because we could probably get back to you quicker. So really appreciate everybody for sticking around, for attending, and I really hope that you found this useful. Please feel free to send me any feedback, and hopefully this fall our goal would be to get kind of complete the trilogy and do a super advanced version of this workshop, of this webinar, because there's a ton of stuff that I just didn't have time to dive into today. So once again, we wish you all the best in all of your DOE work, and have a good rest of the day or evening, and we hope to see you soon. So thanks again, and bye-bye now.